Hello, my dears. So in our last lesson, we started understanding a little bit more about waves, and we introduced and defined a bunch of different terms like amplitude and wavelength and frequency and period and medium and all these things. Our goal for this lesson is to dive in a little bit deeper with those different parameters of waves and try to understand a little bit more about the relationships among those different wave characteristics. So to do that, you should have already completed the 8.2 investigation, where you actually got to play with a simulation and see how some of these different parameters relate to each other. And then in this video, we're just going to kind of summarize the findings there and put it all together in a nice, neat package. All right, cool. So first investigation that you did was looking at the relationship between frequency and period. So which of the four patterns that we have been talking about this year, linear, quadratic, inverse, or inverse square, which of those four patterns best describes the relationship between frequency and period? Frequency and period have a nice inverse relationship with one another, that as one goes up, the other one goes down by the same factor. And in fact, this is a really simple inverse relationship in that frequency and period are just the inverse of each other. So period is equal to 1 divided by frequency. Frequency is equal to 1 divided by the period. And that kind of makes sense if we just think about the definition of each of those terms, because frequency is describing the number of cycles per second, period describes the number of seconds per one cycle. So they're just flipped, but otherwise the same sort of thing there. Okay, so inverse relationship between frequency and period. Now, just to kind of solidify our understanding there, let's consider this slightly twisted sample problem. So we've got a kid swinging from a tree branch on a rope. So we've got this rope swing here. Kid's supposed to jump off at the other end of the swing, but freaks out and instead hangs on to the rope swing and then swings back and runs into the tree. And that happens a few more times. So anyway, our poor kid, who is clinging desperately to this rope swing, keeps swinging back and forth and ultimately hits that tree branch 5 times over the course of 10 seconds. And so our question naturally as physicists is, well, what's the deal with that swinging? What's the period of the swinging, and what is the frequency of the swinging? And then we'll tend to the child's well-being later. Okay, so let's start with the idea of period. Now, you might look at this and see this 10 seconds number and assume, okay, well, that's a time measured in seconds. That must be the period. But remember that period describes the amount of time it takes to complete just one cycle in this oscillating motion. And we see that 10 seconds is the amount of time it took for the child to swing out and back again 5 times rather than just once, okay? So in order to figure out the period, the amount of time for just one cycle, one swing out and back, we're gonna set up equal proportions here. So the period is the time for one cycle, and 10 seconds is the time for 5 cycles. And so those should have equal proportions there. So then we can just cross multiply and divide through and ultimately determine that the period of that swinging is 2 seconds. So each swing out and back again takes a total of 2 seconds. 1 second to go out and another 1 second to come back again. All right. So that's the first question there then. Now that we know the period, to calculate the frequency, we're just going to do 1 over the period. So 1 over 2, the child swinging has a frequency of 0.5 hertz. Every second the child completes 1/2 of the cyclical journey, just goes out or just goes back again. So that was our first investigation, looking at the relationship between frequency and period. The next investigation, or next part of the investigation, dealt with the relationship between frequency and wavelength, and starting to sneak in a little bit of wave speed in there as well. So same question as before. When we look at the relationship between frequency and wavelength, is that relationship best described as linear, quadratic, inverse, or inverse square? Once again here, we see an inverse relationship, that as frequency goes up, wavelength goes down by the same factor, or vice versa. Now, I asked you to try for each row of your data table multiplying the frequency times the wavelength, and you should have found an interesting pattern emerging as you did that. What did the frequency times the wavelength always equal? Frequency times wavelength will always give us the overall speed of the wave, how quickly it is propagating through space. So that's cute, and we're going to look at an equation that sums that up in just a moment there. But first, given this relationship then that we see frequency times wavelength equals wave speed, did you find that changing the frequency changed the wave speed? What we should have found is that despite the fact that frequency times wavelength equals wave speed, and so you would think that there's a relationship between frequency and wave speed is actually independent of both frequency and wavelength individually. And the reason for that is because of that inverse relationship between frequency and wavelength. So what you should have found is that if you increase the frequency, the wavelength goes down. And so those two changes end up canceling each other out, and the wave speed doesn't change. So if frequency doubles, wavelength halves, and then you multiply those two together, and those two factors end up canceling each other out. So we should find that changing frequency and changing wavelength, and therefore also changing period, have no effect on the wave speed. The wave speed stays constant through all of those changes. And so this brings us then to our wave speed equation. So we did find then that the speed of the wave is always equal to the frequency times the wavelength, but that can be a little bit of a weird way to think about it since wave speed is being held constant for a given situation. So what might be easier, an easier way to think about it would be the first equation here. The frequency is equal to the wave speed divided by the wavelength. All right, so V represents the speed of the wave in meters per second, just like any other speed we've talked about. F represents the frequency in hertz, and then wavelength is represented by this funny little Greek letter, which is a lowercase lambda. All right, so we've got this little lambda representing wavelength in meters. So another little sample problem for you. So the speed of light going through a vacuum, through empty space, because light is our one non-mechanical wave here, is about 3 times 10 to the 8th meters per second, or in other words, 300 million meters per second, which is kind of fast. So given that information, what is the frequency of a green light wave? And green light waves are in the vicinity of 510 nanometers long. All right, so to figure this out, let's go ahead and go through our guess method, list everything that we know. So we know that the speed of the light wave is 3 times 10 to the 8th meters per second. We know that the wavelength of that light wave is 510 nanometers. Now, I can't quite start plugging things into my equation yet because I see that there is a mismatch between my units. I've got my velocity or my speed in meters per second, wavelength is in nanometers. We got to get those into the same units. So 510 nanometers, now nano means times 10 to the negative 9. Okay, so 1 nanometer is equal to 1 times 10 to the negative 9 meters. Therefore, 510 nanometers is 510 times 10 to the negative 9 meters. And if you are a stickler for scientific notation, you just got to do it correctly, you could also rewrite that as 5.1 times 10 to the negative 7 meters. You could do either one, either of those two representations is fine as long as your wavelength is in meters. Right? So we've got speed, we've got wavelength, their units match up at this point. We are trying to calculate frequency. To help us do that, we've got our wave speed equation. So frequency is going to be equal to speed of the wave divided by wavelength. So we go ahead and plug that in, being sure if you're using your calculator to put parentheses around your entire denominator as shown there. And we end up determining that the frequency of a green light wave is on the order of 5.9 times 10 to the 14 hertz, which means that these electromagnetic waves for green light are oscillating at a rate of 6 times 10 to the 14 times per second. So, you know, that's pretty frequent. That's a pretty high frequency. Cool. All right. So then at this point, we have determined from our investigation that amplitude has no bearing on wave speed. That was our third part of the investigation there. We've already established that frequency, period, wavelength, none of those changes the speed of the wave. So our question then is, what actually does influence how fast a wave is moving through a given area? And it turns out there's just one determinant for that wave speed, and that is the medium that the wave is traveling through. The material that our wave is traveling through is really what dictates that wave speed, because our wave is going to basically just move as fast as it is capable of doing within the limits of the material that it's in. That the medium has the ability to kind of slow it down, limit how fast our wave is able to move through it. So really then the material is sort of our big limiting factor for how fast our wave is capable of moving. Now to predict a little bit more how medium affects the speed of a wave, a couple things for us to consider. So mechanical waves, again, require a medium to propagate at all, right? So mechanical waves pass through particles, through objects, interacting and passing energy along in the form of that wave. So basically then mechanical waves are going to travel fastest when particles are able to transfer energy efficiently, when we've got our particles close together enough to be able to transfer that, when they're moving quickly enough that they're kind of able to bounce into each other and transfer that energy. But we really want our particles able to be interacting on a regular basis in order to allow that mechanical wave to move as quickly as possible. Now, non-mechanical waves, like light, on the other hand, travel fastest in a medium where we have less in the way of particles, when there's a lower density of particles. Because again, non-mechanical waves, light waves, don't need a medium in order to travel through it. So really particles are just kind of there getting in the way to some extent, kind of taking that energy and using it and absorbing it and reflecting it and doing all sorts of things. And so really then light waves move fastest when the particles just get the heck out of the way of them moving. So some of the factors then or some of the characteristics of a medium that will influence wave speed then are obviously the type of material, but also then things like the state of matter. So for example, sound waves move faster through solids than they do through air, which seems kind of weird, but if we think about a solid, the particles are more densely packed together. It is easier for particles to bump into each other to transfer energy along than it is in air, where there's a lot of distance between our particles and it's less common for them to collide with each other. Okay, density, as I've already mentioned, temperature, which influences how quickly our particles are moving and how readily they are able to collide. So those are some of the ways then that the characteristics of our medium really determine the speed of the wave traveling through that medium. Okay. So final little check for understanding. Say we've got a sound wave moving through the air. Which of these different options will slow down that sound wave? Should we make it louder, raise its pitch, lower the temperature of the air, or redirect that wave through water instead of air? The one option that will slow down our sound wave is option D, lowering the temperature of the air. So to unpack that a little bit, the first three options here, so making it louder means changing the amplitude, changing the pitch means changing the frequency, which in turn also changes the wavelength and the period, but ultimately none of those is going to affect the speed of the wave on its own, as we have established. Okay, so amplitude, wavelength, frequency, period, all of those on their own, we change them, it doesn't change the speed of the wave. Option E would change the speed of the wave, sending it through water instead of air, because we're now changing the medium. But for a mechanical wave, like a sound wave here, having the wave travel through water is actually going to speed up our wave instead, because in water our particles are more closely packed together than in air. Air, it's much more space in between our particles, fewer opportunities for collision. So by sending the wave through water, the wave will actually move faster if we do that. But the one option that will slow down the sound wave is lowering the temperature of the air, because if we lower the temperature of the air, those air molecules are moving more slowly. That means fewer opportunities for collision, and it means it's less efficient for that sound energy to pass from one particle to the next. All right, I think that's all I've got for you for now. That's it. I love you. Have a wonderful day.